Okay. I will wind up the discussion of the ideal gas. There's just something very brief I want to go over. Okay. We wrote the last time that pressure times volume, we derived this was equal to N times the average value of M V square over 3, okay, from Newton's laws. And we noticed that from experiments, from empirical measurements, it was known that PV also equaled N times the temperature. And there was some proportionality constant that depended on how you define the degree in temperature. So when this thing is in degrees Kelvin, okay, which means temperature of something in degrees Kelvin is temperature in degrees centigrade plus 273, all right. Then K was equal to 1.38 times 10 to the minus 23 joules per degree Kelvin. K times T is an energy, clearly, because our theoretical derivation from Newton's laws told us that its meaning is just 2/3 of the kinetic energy, right? So it must be in joules. Okay, now N here is the number of molecules in the gas, so it's a very large number. Let's see what this N is. Consider a gas of mass m grams. I'll use grams because kilogram is not a good measure for a gas. Gas is usually, a huge amount of gas will be a few grams, right? Huge volume of gas will be a few grams. So let's say m grams. Then, and suppose we have of molecules of molecular weight, let's say mW. We'll see what that means. Then N is simply the total mass, number of atoms is, or number of particles, number of pieces is the total mass. You have 200 grams of gas there, and you divide it by the mass of every little particle there, okay? And that mass is, of course, going to be very small. And how much is it? It will be some multiple of the mass of the hydrogen atom. Hydrogen atom is the smallest atom. It's just one proton and one electron, as we now know, okay? And we know from experiments how to weigh the atoms. These experiments became possible at the beginning of the 20th century. So quite late in developing science, it became possible to measure masses of atoms. Anyway, the mass of the smallest atom, the mass of the hydrogen atom, in our units is, this thing equals 1.6 times 10 to the minus 24 grams mass of hydrogen atom. So what does molecular weight mean? If you have H atoms, hydrogen atoms, molecular weight equals 1. Every little particle is just one atom. If you have H2 molecules, what is the molecular weight? It's just how many units of hydrogen atom mass it has, right? It's just 2. Oxygen atoms, one oxygen atom contains 8 protons and 8 neutrons. So its weight is 16 times the mass of the proton. So 16 times the mass of the hydrogen atom, right? So molecular weight is 16. If you have O2 molecules, molecular weight is 32 because it has 2 oxygen molecules. Each particle contains 2 oxygens and each one contains 16 little units of hydrogen mass. It's a very simple idea. The basic unit of counting mass among atoms and molecules is just chosen as the mass of the smallest atom, which is hydrogen. So if it's 16 times as heavy as hydrogen, you say its molecular weight is 16. Water vapor, steam, has particles of H2O. So what's the molecular weight of that? 18, right? And so on. So let's continue now what that gives us. So the number of particles in the gas is mass in grams divided by molecular weight, okay, times 1.6 times 10 to the minus 24 grams. All right? What that gives you you just take the mass in grams divided by the molecular weight, and you have a number there which is 1 over 1.6 times 10 to the minus 24. What is that number? How many little hydrogen atoms will make up together 1 gram? If you divide 1 divided by 1.6 times 10 to the minus 24, that gives you just a number. Okay, the number of hydrogen atoms that will altogether make up 1 gram. And that number is called by somebody's name. It's called Avogadro's numbers. Some of you may have heard it. Its meaning is very simple. Our daily life unit of a gram contains how many atomic units? Okay? And what is the meaning of this mass of gas divided by molecular weight of the molecules? This is called the number of moles. This is going to be just a number, right? If you have 200 grams of gas and it's made up of, let's say, oxygen molecules, O2, so you are dividing 200 by 32. It will give you some number close to 7, okay? So every different molecule has a different measure because it contributes so many units of the hydrogen atom. And this thing, mass in units of the molecular weight, is called the number of moles. What does that give me? Let me call this number of moles N. the total number of particles in the gas will be the number of this basic unit mole, the number of moles, times this number, called an Avogadro. So I have this 6.02 times 10 to the 23, a magic number. Now if you go back to the gas law, we had PV equals NKT, which is number of moles times 6.02 times 10 to the 23 times 1.38 times 10 to the minus 23, right? Joules per degree Kelvin. All of this stuff times T. So we can write as PV equals N times, and give this number a name, R, N, RT. So sometimes you will see the same gas law, pressure of the gas times the volume of the box that contains the gas equals the number of little particles times kT, or you count the number in terms of how many Avogadro numbers. Okay? Then you have to know the number of moles, which may be 2, 5, 10, not a very large number, okay? Number of moles times another constant R. So sometimes you see it PV equals little n RT. It's the same thing. Essentially, P times V is proportional to T times the number of things, and there are different ways of counting how many little particles you have. That's all. Okay? This shows up in problems having to do with ideal gases, so you better know that there are two different constants and different ways of counting. It's not a difficult thing. All right? Any questions on this? Okay. Now we start a new module of the course. We are starting electricity and magnetism. Now, from the earliest science on record, from the ancient Greek philosophers, they were making some experiments with matter. And one of the things that these people realized was a simple fact that if you take two pieces of matter, like some cloth and some glass, okay? They had textiles, of course. They were quite advanced civilization already. So they had these things. And rub them. Then separate them. You find that after rubbing, these things acquire a new property. Two such pieces of silk that have been prepared by rubbing against glass or whatever, if you try to bring them together, they will push each other apart. And they found that it was possible to give this property in two different types, two different kinds, so that things with the same property repelled and things with opposite such property attracted. This thing is a new property of nature, and they called it charge. Okay? And the word electric also came from these early days, because one of the things that they used very frequently, because it charged up easily by rubbing, was amber. Amber veya kehribar, değerli taş. Okay? And its name in Greek was electric something. So the name electric comes from the semi-precious stone amber. All right. Now, so it was a mysterious property of matter. They didn't really know what. Mass, they understood, people understood, had something to do with quantity of charge. The more you added the quantity of matter, the more you have mass, okay, the more you add matter, the more massive, the more weight it has. But charge, what is charge? You have to do something funny. Unless you rub, you do some special preparation. Ordinarily, there is no charge on matter. But when you make some effort, certain types of materials will have a separation of this property. One end acquires one type of charge, and the other one then has the opposite type of charge. Okay? So this is called, one type of charge is called minus, and one type is called plus. But of course, for a very long time, it wasn't understood why. What was it? It's some kind of intrinsic possibility in matter, which ordinarily doesn't show itself. If you do something, these two opposite natures in it separate out physically. Okay? And then if you leave it alone, if you rub a piece of amber, it has minus and plus sides. If you leave it alone, after a while, it has lost this property, the minus and plus. Okay? It's obviously something going on which, if you make a special effort, you can separate into two types, but they soon join back together. Okay? And they didn't, scientists, until the end of the 19th century, quite a while after physics and chemistry had developed, they were not able to isolate what was the basic carrier of this charge. Only in 1895, which is quite late, it's a little more than 100 years ago, okay? An experimental physicist, J.J. Thomson, was able to separate negative charges and show that this was a type of particle, very, very small particle. He discovered the electron. Before that time, it was already known, or it was debated, people had quarrels over this, that matter must be made of very small building blocks that they called atoms. The idea of the atom, as you will know, as you will learn from your readings this week, is probably the most important idea in science. The essay you will read is an essay by the famous physicist Feynman, and it's his thesis that if there was just one idea, if civilization were to be destroyed and there was one idea to be left from our culture to some other civilization, to describe what we know, what we have figured out about nature, Feynman thinks, he's probably right, that our main, most important idea, central idea in science, is that all matter is made up of pieces, atoms. Now it seems very natural to us. You might say, well, why not? But historically, the idea, the speculation about the atom is very, very old, again dating back to the ancient Greeks and perhaps even earlier. But the actual proof that you could separate matter into constituent atoms You could isolate atoms, you could weigh the atoms and figure their constituent particles and their charges and so on. This became possible only at the end of the 19th century and beginning of 20th century. For example, the measurement of Avogadro's number, or the measurement of the atomic mass, involved an experiment called Brownian motion, which was explained by Einstein, which showed a way of figuring out from experiments what Avogadro's number is. So the direct proof of atoms and electrons and so on is quite recent, although the idea was there. Anyway, when the electron was discovered, scientists finally understood what is charge. At least where charge resides, where charge is carried. Charge is a fundamental property of the basic constituent pieces of matter. Okay, so when you split the atom and you separate an electron, then that has charge. Arbitrarily, just by convention, the charge of the electron was called the negative type. So what is left in the atom is positive charge. Positive charge is carried by protons. But it was only, again, at the end of the 19th century, that it was possible to see what the structure of the atom was, and that these electrons were very light, small mass particles. The atom was a lot heavier, and the mass of the atom was carried by other objects which were concentrated at the center. It was discovered in the 1930s, again, even more recently, okay, that there were two types of heavy particles in the atom, the neutron and the proton. The proton carried plus charge opposite to the electron, and the neutron was carrying as much mass as the proton, okay, but it didn't have charge. It had zero charge. Now, a really interesting property of charge is that the electron and the proton charges are equal in magnitude. They are opposite types, one is minus, one is plus, but the magnitude of the basic charge, basic plus charge, the unit of plus charge, the charge carried by the proton is exactly the same as that carried by the electron. Okay? So that when they form atoms, there must be same numbers of protons and electrons, so that the atom is neutral. All right? Now, this is our understanding of charge. Essentially, we now know that charge is quantized. It has a basic unit, the electron charge, and every other charge on particles is plus or minus that. Some particles, some atoms, some ions have 2 plus 2 charge or minus 2 charge or whatever, but there is no such thing as something carrying a basic particle, that is, carrying a charge of minus 2.37. It has to be integer, plus or minus so many units of charge, okay? Again, this may seem simple because you have already heard it, but it doesn't have to be so. This is something that was discovered very hardly from experiments, okay? Now, there's one exception, quarks. If you ask what makes up a proton, it seems from experiments involving very high energy collisions of these particles that protons have inside them 3 little pieces that make up this proton, 3 pieces. This is what's called a quark, and the quarks have charges of plus or minus 2/3 or 1/3 units. So they don't have integer charge. But the funny property that quarks have is that you infer they have such 2/3, 1/3 charges, but you can never isolate a quark, take it out of its proton or neutron. So anything that you see as an isolated charge is always plus or minus 1, 2, 3, 4 integer number of electron charges. Okay. Now that is how we understand charge. But of course, before charge was understood, as soon as charge was discovered by rubbing silk or glass or whatever, its property of attraction or repulsion, making things move or changing their motion, was discovered. And after Newton, after mechanics was discovered, the notion of force, and force is something that gives you acceleration. When that was discovered, it was possible, of course, to measure exactly what kinds of forces do charges cause. Okay, because you just bring together two charges. If they are the same type of charge, they will repel. All right. That was it as far as the ancient Greeks were concerned. But after Newton in the 18th century, it was possible to charge objects, to let them interact, to measure their acceleration, and you know their mass, so then you can figure out what is the force that one charge gives on this other charge to accelerate it to the extent that you measure. Forces are possible to measure. Okay, so this is the discovery of the force electric force by Coulomb. If you have two charges, you measure how much the charge is in some kind of unit, okay? And the force between the two charges is proportional to the amount of charge on each of these guys, divided by the distance between them. Depending on your system of units, how you define the unit of charge, there is going to be a proportionality constant in front. Okay? And the direction of this force, just like gravity, is along the line joining these two charges. So if this is where Q1 is sitting and this is where Q2 is sitting, this is R. The length of this vector is 2 meters, 3 meters. In my case, about 1 meter, okay? And what I mean by R hat, you will remember from the beginning of the course, it just means direction. So the force is directly along this line. Whether it's attractive or repulsive comes out of the formula anyway, because if Q1 and Q2 are both positive, the result will be in the direction of R. How do I define that direction? Along the line, and if I choose one of my particles to be at the origin 0, then R is pointing to the other particle. If both charges have the same sign, it will be in the direction of R, therefore away from the other charge. Repulsion. All right? If Q1 is negative and Q2 is positive, then of course you get a minus sign there. Minus 3 times plus 5 is minus 15. Okay? In that case, there will be attraction. So without putting a plus or minus, but remembering that Q1 and Q2 themselves can be plus or minus, this formula tells you that you can have attraction of opposite charges and repulsion of the same type of charge. 2 minuses or 2 pluses repel each other. Okay. Now let us define units. The unit This was discovered, is named after a French physicist called Coulomb, 18th century, early 19th century. Okay. So this is called the Coulomb force. And in the honor of Coulomb, there was some old definition of the unit of charge that was named the Coulomb, this thing. This is the unit. And in that unit, the basic charge of the electron is 1.6 times 10 to the minus 19. Okay? It just says that the Coulomb, which was defined in macroscopic daily life experiments, like rubbing some glass and silk, can bring together charges, can pull apart charges. 1 Coulomb, typically, is much, much larger than the charge of a single electron. So your usual rubbing of amber or glass or whatever must involve separation from the matter to one side of something like 10 to the 19 electrons. That's a lot. It's not all the electrons, because in a macroscopic piece of matter, you will typically have as many particles as the of the order of the Avogadro number, which is 10 to the 23. Okay? But 10 to the 19 is like to charge something up macroscopically. 1 out of every 10 to the 4, 1 out of 10,000 electrons is being pushed out. Okay? So the moral from all of this, the summary is, the kinds of charges we can handle in our daily life, in the macroscopic world, are huge in terms of the particle charges. The charge of the electron in our macro units is 10 to the minus 19. Okay? This constant in front, that I called K, the proportionality constant, in our SI system of units, is sometimes written not just as K, but in terms of another constant that's called epsilon 0. K is defined as 1 over 4 pi epsilon 0. This may sound strange. The reason you will see later in a few more lectures, you will see that we will derive from this force some other formulas in which 4 pi appears and cancels this. Okay? So it's arbitrary how you give a name to something. Instead of calling it K, sometimes we call it, its name is 1 over 4 pi epsilon 0. All right? Let me, of course, I don't memorize these things. Let's go to the lecture notes and give you the numerical values of this. But I'll give a break now. Okay? And you can each write down what you do not understand before going